few ideas. Come back. Welcome back to our channel Machinery and Technology. Today, we have a truly electrifying topic to delve into. Railway construction technology. Is rail transport only necessary for industry? Of course no. Tanks and military vehicles can be transported quickly by rail. Another advantage of railways is that damaged railway lines can be activated quickly after natural disasters such as earthquakes. With just a few ideas above, you can see the importance of railways for each country. So, if you're ready to spark your curiosity, let's dive right in. The journey of a railway track begins with raw steel, transformed into the familiar grooved rails that guide massive trains. Molten steel is poured into molds, solidifying into large blocks called blooms. These blooms are reheated until pliable, ready for shaping. In a rolling mill, the hot bloom is squeezed and guided through a series of rollers, progressively pressing it into the distinctive I-beam profile, the heart of a railway track, complete with a head, web, and base. Once shaped, the rails are meticulously cooled to prevent warping, using controlled air or water quenching. Rigorous inspections follow, employing advanced techniques to detect any hidden cracks or imperfections. Finally, the long rails are cut to precise lengths and meticulously drilled to be secured to the supporting sleepers. The finished product may undergo additional treatments for a smooth surface and a protective coating to ensure a long and reliable lifespan. Modern railway track production relies heavily on automation and cutting-edge processes, guaranteeing consistent quality, strength, and precise dimensions, every step meticulously controlled to create the foundation for safe and efficient train travel. Traditionally, tracks are constructed using flat-bottomed steel rails laid on and spiked or screwed into timber or pre-stressed concrete sleepers, known as ties in North America, with crushed stone ballast placed beneath and around the sleepers. Most modern railroads with heavy traffic use continuously welded rails that are attached to the sleepers with base plates that spread the load. When concrete sleepers are used, a plastic or rubber pad is usually placed between the rail and the tie plate. Rail is usually attached to the sleeper with resilient fastenings, although cut spikes are widely used in North America. For much of the 20th century, rail track used softwood timber sleepers and jointed rails, and a considerable amount of this track remains on secondary and tertiary routes. In North America and Australia, Flat-bottomed rails were typically fastened to the sleepers with dog spikes through a flat tie plate. In Britain and Ireland, ball head rails were carried in cast iron chairs which were spiked to the sleepers. In 1936, the London, Midland and Scottish Railway pioneered the conversion to flat-bottomed rail in Britain, though earlier lines had made some use of it. Jointed rails were used at first because contemporary technology did not offer any alternative. However, the intrinsic weakness in resisting vertical loading results in the ballast becoming depressed, and a heavy maintenance workload is imposed to prevent unacceptable geometrical defects at the joints. The joints also needed to be lubricated, and wear at the fish plate, joint bar, mating surfaces needed to be rectified by shimming. For this reason, jointed track is not financially appropriate for heavily operated railroads. Timber sleepers are of many available timbers and are often treated with creosote, chromated copper arsenate, or other wood preservatives. Pre-stressed concrete sleepers are often used where timber is scarce and where tonnage or speeds are high. Steel is used in some applications. The track ballast is customarily crushed stone, and the purpose of this is to support the sleepers and allow some adjustment of their position, while allowing free drainage. Modern track typically uses hot-rolled steel with a profile of an asymmetrical rounded I-beam. Unlike some other uses of iron and steel, railway rails are subject to very high stresses and have to be made of very high-quality steel alloy. It took many decades to improve the quality of the materials, including the change from iron to steel. The stronger the rails and the rest of the trackwork, the heavier and faster the trains the track can carry. North American railroads until the mid to late 20th century used rails 39 feet, 11.9 meters, long so they could be carried in gondola cars, open wagons, often 40 feet, 12.2 meters, long. As gondola sizes increased, so did rail lengths. As we all know, railroad tracks are produced with certain lengths, such as 12.5 meters, 25 meters, and the length-thin ones from 50 meters to 100 meters. No matter how long the railroad rail is, they need to be joined end to end to make a continuous railroad. This can be realized by rail joints, joint bars, or welding methods. The principle of railroad thermite welding. Railroad thermite welding is a welding method that uses the heat of chemical reaction as the heat source. When welding, the ends of the two rails are fixed in the mold in advance, and then the mixture of aluminum powder and iron oxide powder, called thermite, is heated in the crucible. An exothermic reaction is producing liquid metal, iron, and molten slag which are injected into the mold. Liquid metal flows into the joint gaps to form weld metal, while slag floats on the surface. To adjust the temperature of the melt and the chemical composition of the weld metal, appropriate additives and alloys are often added to the thermite. Equipment and auxiliary material preparation, consuming material, thermites in crucible sealing mud, high temperature matches, grinding wheel, propane, oxygen, hose, auxiliary equipment, mold, slag tray, crucible fork, sand mold fixture, sand mold cover, 1 meter leaning ruler, rail thermometer, clamping device, crowbar, preheat frame, steel wedge, auxiliary machinery, rail saw, polisher, portable grinder, etc. Railroad track preparation. Unload the 2 to 4 pairs of rail fasteners on both sides of welding end. Rail end cleaning and drying. Use the portable grinder to remove rust and decontamination of rail end. Make sure the face of rail ends to be welded is dry and clean. Rail end alignment. The width between the rail end face needs to be 27 mm 30 meter. The vertical and horizontal alignment of the rail head, rail web and rail base is required. Fixture installation. The fixture should be installed in the upwind direction. Sand mold installation. The pouring hole is slightly trimmed to prevent sand particles from falling off during preheating and pouring, resulting in welding slag. Install the bottom plate first, then install the side mold. Finally, use the clamp to fix the skin mold. Sealing. Apply sealing mud to the outlet of the skin mold and the thread of the fixture to make the skin mold and the rail tightly sealed. Preheating. Firstly, regulate the working pressure of propane and oxygen. Secondly, install the heater on the frame. Adjust the nozzle to the center of the sand mold and place the shunt plug on the edge of the sand mold. Remove the heater from the support and ignite the nozzle. Thirdly, regulate the pressure and mixing ratio of propane and oxygen to get the best flame. Finally, preheat for 5 minutes. Crucible installation. This step is prepared at the same time as the preheat. Mix the thermite evenly, pour them into the crucible. Insert the high temperature match and then cover the crucible. Ignition. Put the crucible on the skin mold right after the preheating is finished. Verify the position and light the match quickly. Thermite reaction. Observe the chemical reaction. When there comes the open flame, it is the starting time for the thermite reaction. As soon as the flame fades out, the chemical reaction stops. Normally, the time for thermite reaction is 8 to 15 seconds.
Show me the money. Sausages, the barbecue up for lunch.
Oh, you wouldn't want to eat the sausage after this? That's alright, we'll let it have a little smolder.
That's it, that's the fun done. Yeah.
Demolding. Remove the sand mold and the slag tray 5 minutes after the pouring of molten iron. Cut off excess thermite. Cut off the extra thermite and bend the ones protruding on both sides of the rail base.
When it's cooled down enough for us, it's easier to glide. It's quick on. So you take it off, Peter?
Yeah, we'll go slowly.
See you, mate.
You see us, we'll cut it here and you get a good look at it.
Yep.
And then we'll cut it again.
Cut from your side. I'll show
Yeah,
it.
the stripping down time. It's a little bit softer. It's a little bit wet. Just slowly coming over. In front of there. Help us shape it up. This should be cutting any excess steel that we don't need. Yeah, we'll cut it, it'll be easier for us to break it off. You'll see once we take it off and we knock it apart, it will be just a round shape itself. You always got to make sure you got a good one of these machines. You know, if you don't, you'll be swinging all day with an axe and a hammer, trying to cut it yourself. Punishment worse. Something you don't want to do. Save it. Really pull it out of the big bubble. Yeah, but it felt loose to me when I was trying to like shake it up a bit. So I thought it was like too wet. Can we?
Grinding. This is the final step of welding railroad rail. This is to make the surface of joined rails flat and smooth. After the 13 steps are finished, check the welding joints to make sure they are up to the standard. Restore the railroad tracks to its original place. Also, there is still some cleanup job to do. Workers need to take away the dust, slag, scrap, sand mold, and the crucible. For mobile welding of continuous welded rails, these machines are normally integrated into an autonomously operating rail welding system. These systems are equipped with diesel generator set, hydraulic unit, cooling unit, and lifting device. Container-based rail welding systems are especially suitable for welding continuous welded rails directly in new railway track. They are also often used semi-stationary in the depot or near the job site for preparation of long welded rails for a section in a new railway line. The truck-based rail welding system is highly flexible as it is self-propelled and can move from one job site to the next within a short time. The traditional method of welding has been aluminothermic welding, which requires a filler material, resulting in a weaker weld, with a longer cooling and solidifying time. Flash butt welding, by contrast, is a solid phase weld, welding rail to rail with no filler material. It results in a far superior weld that is stronger in every way. It is better in terms of fatigue and the flexibility of the material. There are no differential material issues and no hardness issues, because it's exactly the same material. Because you don't have to have a collar configuration, you've got a stronger weld. The weld uses basic electrical processes, using a short circuit to create heat, then forging the metal together. The machine's maximum amperage is about 1000 amps, though during the weld cycle it is typically at 600 to 700 amps, reaching temperatures of 800–900 degrees Celsius. The flexibility of the machine means it can be positioned on the track, on the adjacent track, line side, in a forefoot, on the road, or even in the factory. One of the most important advances of this latest technology is the ability to do simultaneous welding and stressing of the rail, saving a huge amount of time. They can complete the production welds and stress in the same shift. The computer has a useful display showing information during the weld, but more importantly collects a vast amount of data during each weld, which can then be analyzed later, especially if there is a problem during production. In recent years, larger tamping machines have been developed that incorporate additional functions such as lining and lifting the rails on top of their tamping function. These are known in North America as production tampers. At its most basic, a tamping machine only packs the ballast. Some modern machines, sometimes known as tamper liners or tamping and lining machines, also correct the alignment of the rails to make them parallel and level, in order to achieve a more comfortable ride for passengers and freight, and to reduce the mechanical strain applied to the rails by passing trains. This is done by finding places where the sleepers have sunk from the weight of the passing trains or frost action, causing the track to sag. The tamper lifts each sleeper and the rails up and packs ballast underneath. When the sleeper is laid down again, the sagged rails now sit at the proper level. Combining tamping and lining into a single machine saves time and money, as only one machine needs to be run over the track to perform both functions. Tampers frequently work in concert with ballast regulators as part of a section crew. In the early days of railroading, the ballast was maintained by hand, with gandy dancers using shovels and beaters to move, clean, and compact ballast. Rails would be jacked up with large track jacks to allow the crews to do their work. This process took quite a long time and was subject to human error. Over time, ballast becomes worn and loses its angularity, becoming rounded. This hinders the tessellation of pieces of ballast with one another, and thus reduces its effectiveness. Fine pieces of granite, like sand, are also created by attrition, known simply as fines. Combined with water in the ballast, these fines stick together, making the ballast like a lump of concrete. This hinders both track drainage and the flexibility of the ballast to constrain the track as it moves under traffic. Ballast cleaning removes this worn ballast, screens it, and replaces the dirty, worn ballast with fresh ballast. The advantage of ballast cleaning is that it can be done by an on-track machine without removing the rail and sleepers, and it is therefore cheaper than a total excavation. Modern ballast cleaner operations. A cutter bar runs beneath sleeper level, excavating all of the ballast under the sleepers to a specified variable depth. A conveyor then moves the ballast into the cleaner, where it gets forced through a mesh by a shaking chamber. Pieces of ballast, which are smaller than the mesh size, fall through and are rejected. Those that are bigger than the mesh are returned to the track along with fresh ballast. Some ballast cleaners have both ballast and spoil wagons attached to it, to which the materials are fed by a series of conveyor belts. Others simply undercut the ballast and allow for a work train to come through to dump fresh ballast. This process can be done in short sections, meaning that track life can be considerably extended with the minimum of disruption. The whole railroad track thing is pretty neat if you think about it. It all starts with a solid base, like a track bed you wouldn't believe. Then comes a layer of crushed rock. That's the ballast, to keep everything level and drain away any water. On top of that goes the real star of the show, the tracks themselves. Each track is made up of a few parts. First, there's the railroad tie, kind of like a big old bed for the rails to rest on. These ties can be wood or even concrete, depending on the situation. To hold the rails onto the ties, you've got fasteners, like spikes for wood ties or clips for concrete ones. The rails themselves are usually steel, all shaped hot and tough. They're measured by weight, like 135 pounds per yard. These days, the rails are mostly welded together for a smoother ride, but back in the day, they were bolted together more often. The most fundamental maintenance of way task is the construction, repair, and replacement of the track and its supporting ballast and grade. In the early days of railroading, this task was almost entirely completed by manual labor. Teams of men, section crews, would be responsible for specific sections of track, each approximately 10 to 20 miles, 16 minus 32 kilometer long. Section crews would manually carry out tasks such as replacing worn-out track components, clearing ditches and culverts, tamping ballast, and removing snow and debris from switches. As the 20th century progressed, large-scale track replacement became an increasingly mechanical task. The spike puller replaced men manually prying spikes out of ties. A team of men with tie tongs manually removing a tie and inserting a new one replaced by a tie exchanger. Manually driving spikes using a spike maul replaced by a spike driver. The adjustment and packing of ballast by hand using shovels and ballast forks was replaced by a tamping machine and ballast regulator. Railroad cranes took over the task of lifting heavy track components such as ties and rails. Most of this equipment could be operated by a single person or handful at most, dramatically reducing the workers needed to carry out a project. The section crew approach to maintenance has disappeared in the United States, with routine track work now carried out by teams of workers trained and equipped to carry out specific tasks like replacement of ties or damaged rails that are sent around a company's rail network. Technology increasing has reduced the number of people needed for the important routine maintenance tasks that section crews needed to do, and in some cases, outright eliminated the job. Workers using brooms and shovels to clear snow and ice from fog of railroad switches have been replaced by propane switch heaters. The increased use of continuous welded rail has reduced joints which require attention and maintenance, such as checking for loose bolts on fish plates, which join non-welded rails together on non-welded, joined rails. Ditch digging and clearing can now be handled by workers using backhoes and excavators, or by specialized rail equipment that digs the ditch as it travels along a track. Train track replacement isn't done by a single machine, but rather a complex system of integrated machines working together called a track renewal train, also known as a track renewal system or new track construction machine. This multi-car train carries all the equipment and materials needed to efficiently replace tracks in a continuous operation. To minimize the time of track during a track renewal project, a track renewal train is used to automate most of the required process. Prior to the arrival of the track renewal train, preparation tasks must be completed. In some cases, the old rail needs to be cut into smaller segments and joined with fish plates. The rail fastening system may need to be released prior to its arrival. The new rails usually need to be prepared prior to the arrival of track renewal train. Rails are delivered to the center of the track. Those rail pieces are welded by track workers to form continuous welded rail, CWR, and left at the center of the track at the exact position required by the track renewal train to pick up at its arrival. The renewal process begins with the methodical removal of the old sleepers. Depending on the type of fastening system used, this might involve unclipping the rails from the sleepers. Some amazing machines even have built-in, semi-automatic clip releasers. These are hoisted by the train itself, allowing workers to position them and effortlessly detach the clips. For older tracks with wooden sleepers, there might even be a dedicated spike-removing machine. Once the rails are unfastened, they're lifted free and pushed to the sides of the train. New rails are fed in nearby, all set for their upcoming installation. The train itself takes care of extracting the old sleepers from the ballast using a special machine that pulls them out. These are then loaded onto conveyors and transported to the rear of the train for storage. Next comes prepping the ballast bed for the new concrete sleepers. Sometimes the bed needs to be lowered, and the train might have a built-in ballast excavator for this job. Any excess material is transported by conveyor belt to a special storage area. Here, the old ballast gets sorted. Usable materials are cleaned and prepped for reuse, while anything unusable is stored separately for disposal. The most impressive part. Some machines can actually copy the old track. By recording the geometry of the rails before removal, they can calculate exactly how much ballast needs to be cleared. This ensures the new sleepers and rails are laid perfectly, matching the original track's cant, level, and position. See those big cranes up top? Those are gantry cranes, and they're what keep this whole operation moving. They ride on special rails that run along the entire train, even connecting between cars. That way, the crew can walk the whole length to keep an eye on things. They grab the old sleepers, Swing them over to the storage area, and then bring the fresh ones right up to the machine. That machine down there? It's like a giant arm, carefully placing each new sleeper on the track bed exactly where it needs to go. Running behind the track replacement machine is the cleaning machine, whose job is to shred and clean up the old tracks left behind by the giant machine in front. Next is the task of the welders. They need to align the rails and make cuts at the rails at the spots that need to be welded, followed by the rail welding process. Here we need experienced workers. This process uses an aluminothermic reaction to create a molten metal joint. A mold is placed around the rail ends, which are preheated. Thermite, a mixture of aluminum and iron oxide, is then ignited, producing extremely high temperatures. The molten metal melts the rail ends and fills the gap, fusing them together. After cooling, the excess material is removed, and the weld is ground smooth. After the track renewal train completes the tasks, the ballast will be put back on the track. For track renewal trains that do not have ballast excavating machines included, workers will use a shoulder ballast cutter machine that takes excess ballast that has been pushed out during the track renewal process into a screening and cleaning machine. The reusable ballast will be put back to the new track together with the new ballast materials. For track renewal trains that do not include track copying or leveling, a ballast tamper will be used to make final adjustments to the track to the correct specification. The ballast regulator will then be used to make the final shape of the ballast.
65 vänster, 28 är det.
28.
Ja.